n, and in fact, once the distance is larger than n, there is no ST path, right, in the residual graph. And that implies that we have a max flow. Yes? And so our idea for achieving this was to use our augmenting paths to destroy any short paths between S and T. So this led us to the idea of the shortest augmenting path algorithm. As a natural way to get rid of short paths, because when you augment along a short path, you saturate one of the edges on it, which destroys that path, right? Now, the fear, what we needed to worry about was that shortest augmenting path doesn't create shorter paths, right? That was the thing we were just wrestling with at the end of the last lecture. We actually are going to want to show a little bit more. We're going to want to show that shortest augmenting path eventually makes paths longer. But we take it in those two separate steps of first demonstrating that it doesn't make anything shorter. And so I'm going to sort of zoom through again the key lemma from last time. If we look at the distances of all vertices, before you do a shortest augmenting path, and we compare them to the distances of all the vertices after you do your shortest augmenting path, then in fact, the new distance is no smaller than the old distance. Okay. And we ran through a proof, right? The essential story is we have a sort of before situation and an after situation. We've got this vertex S. Nothing changes in S before and after. But let's consider, for contradiction, let's consider all vertices that get closer. And let's take V to be the one that is closest after the augmentation, i.e. it has the minimum d prime of V over all of the, am I too loud or is this good? It's good? Okay. So we want to, we look at, we're assuming for contradiction that some vertices do get closer to S. And now we say consider all of them, take the one that got the closest of all. Okay, so this vertex was somewhere before the augmentation, and we know that it got explicitly closer, right? In other words, d prime of V is at most d of V plus 1. Sorry, minus 1. Right? So now as we unpack this, right, let's consider in the after case the shortest, let's consider the shortest path from S to V, and let's let W be the predecessor of V on the shortest path. Defining d prime of v. Okay, so what do we know about w? Well, by definition of shortest path, right, w is one step closer to s, because that's what defines the distance of from s to v in the after situation, right? So there's an edge from w to v, right? And we know that d prime of w is equal to d prime of v minus 1, right? But what else do we know about w? Yes? Right, w has a smaller distance than v afterwards, and that means that it's not in the set of vertices. It's not, I mean, it can't be in the set of vertices that got closer because v was the closest one. So w did not get closer. That means in the before situation, w was, you know, maybe closer to s than it ended up, but certainly no farther from s than it ended up, right? So we have, you know, at least one, or we have equal to one distance here, and we have at least one distance in change in v. Okay. Now we put these together, and this tells us that in the start, right before we did the augmentation, there's a distance of at least 2 between w and v, right? Okay. Now, the next question we have to ask is, how did we end up with this situation that afterwards there is an edge from w to v? Okay. So could the after edge exist before the augmentation? Yeah? Exactly. If there was this edge from w to v, right, that would create a path to v whose length is 1 more than w, which would make the distance between, which would mean that v is not where it should be, right? V should only be 1 step away from w instead of being 2 steps away from w, right? So the answer is no, because it would make w closer than it actually is to s before. Yes? So this edge from w to v is created, right? It didn't exist before. It exists after, which means it was created. What creates a residual edge? Yeah?
Being the bottleneck of shortest path.
It doesn't have to be the bottleneck, right? It doesn't have to be a bottleneck at all, right? What in general leads to the creation of a residual edge? Yeah?
Pushing flow through the opposite direction.
Exactly. You create a residual edge by sending flow in the opposite direction, right? Where previously there was none, right? So we can conclude that WV was created by the shortest augmenting path sending flow on the edge WV. Okay. Now, could the shortest augmenting path send flow on the edge from W to V? Well, what do we see here about the relationship between W and V before the augmentation is carried out? Yes?
W is equal to d of v plus 1.
Right. W is closer than V to S, right? So what we concluded here is that the shortest augmenting path did this, right? It has to trace, oh, I'm sorry, wrong way. The shortest augmenting path did this, right? Sorry, did I invert something here? WV edge, so we sent flow on VW. Right, that's what created the WV edge. Okay, so yes, what I drew is correct. What we've concluded is that our shortest augmenting path looked like this. Right? Is that possible? Well, it's not. By our own definition, by what we've concluded about the relative distance of W and V from S, right? If W is closer to S than V is, then the shortest augmenting path can't go to V and then to W, right? Because it's going to include a shortest. It's going to have the shortest path to W as its first step, right? A shorter augmenting path would just do this, right? So we've concluded that the augmenting path that we found was not actually the shortest augmenting path. And so that gives us a contradiction. Okay. So in particular, VW has to be on the shortest augmenting path from S, which is not possible, since, in fact, W is closer to S than V. So that's a recap of our proof that no vertex can get closer to S. And by exactly the same argument, no vertex can get closer to T either. So if no vertex is getting closer to S or T, that in particular means that S and T aren't getting closer to each other, right? But now we need to show that they get farther apart over time, right? We don't want to be doing this forever. So we can build on the previous lemma and say that after at most mn over 2 augmentations, let me say shortest augmenting paths, the distance from S to T is larger than n, or greater than or equal to n. And so we're done. Okay. And the proof is actually quite similar to what we've already proven about distances not going up. Okay. So the point is that each shortest augmentation saturates some bottleneck edge, right? We always do a saturating augmentation. So some bottleneck edge got saturated, okay? So that edge is gone, right? If we're gone forever, then we'd be very happy because we'd be talking about progress we've made towards finding a max flow. But it might not be gone forever. It might come back later, okay? But what has to happen in order for that edge to get saturated again? So before that edge repeats as the bottleneck edge, what has to happen? So we had this edge VW, and that edge was saturated by a shortest augmenting path. If that never happens again, we can say, great, we've made progress, right? We've made 1 over m progress towards a max flow if we've saturated an edge for the last time. But maybe it's not the last time. What has to happen before it gets saturated again? Yeah? Right. So in order for this edge to become saturated again, just to break down what you've argued, it has to get some capacity back, right? As long as it's saturated, we're not going to use it again. So for it to become saturated again, it has to regain some capacity. Right? How does it regain some capacity? Yes.
When WV is also short.
Right. We must use WV on a shortest augmenting path. Okay. So how does that play out? Right? So at the moment, right, when we use VW, we know that the distance of W is equal to the distance of V plus 1, because it's on the shortest augmenting path. Right? Similarly, when we use WV, right, we've got some other distance functions where it reflects the opposite directions, right? But how can this happen? Like, what are the relationship between the primed distances and the unprimed distances? We know that none of the distances ever decrease during shortest augmenting paths, right? So in particular, we know that d prime, let's see, let me get this in the right order. We know that the prime distances are larger than the unprimed distances, or no smaller, right? So in particular, d prime of W is at least d of W, right? So we can say that d prime of D is at least d of W plus 1, right? So yes, there's what's the contradiction? Sorry, it's not a contradiction, actually. It's just an inference, because we're not making any assumptions to contradict yet. But d of W, you said, was equal to d of V plus 1. So we can write this as d of V plus 2. Right? So before we reuse the edge, the distance of V has to grow by 2. Okay, now that's the tail of the edge, right? Has to get 2 farther away before we use it again. Okay. So the summary is, before we reuse VW, the distance of V increases by at least 2. Okay? Now, how often can the distance of V increase by at least 2? Yes?
N over 2.
N over 2 times. How come?
Because you can't visit another twice the shortest path.
Right. Because the distance of V can't be more than N. That was our argument for why we're trying to increase the distance, right? D of V is never more than N. And that means that there are at most N over 2 increases by 2, which means that there are at most N over 2 saturations of edge VW. Right? And if each edge can only be saturated, right, every augmentation saturates some edge, which means that there are at most m times n over 2 saturations, since each saturation has to be accounted to some edge. And that completes the lemma. Clear? No questions? All right then. Well, this lemma was all we needed, right? So we know we can compute shortest augmenting path in order m time. We know that there are only mn over 2 shortest augmenting paths, and that means that the runtime of the shortest augmenting path algorithm is order m squared n. And there is our strongly polynomial Maxwell algorithm. Feels anticlimactic, but it's actually quite an achievement. This was due to Karp, I think, sometime in the 80s. One of his famed accomplishments. Okay. All right, so now we have a strongly polynomial Maxwell algorithm. Notice how it compares to the weakly polynomial Maxwell algorithms, right? So weakly polynomial, or sorry, thinking all the way back, when we're talking about unit capacity graphs, right? There, the total flow is bounded by n, and so it takes mn time to compute a max flow. More generally, it takes m times f time to compute a max flow in graphs with unit capacity edges, right? That gives us an mn bound for unit capacities. Now, if we're going to have capacities, right, instead of mn, we're looking at m squared. So it's slower in terms of the graph size. Also, there's this log u term, right? But we've already gone from mf to m squared. To get strong polynomiality, we replace the factor of log u by a factor of n, right? So this is, I mean, this could be n to the 5th. So this is not a wonderful running time, right? And so that points us at our next goal, which is to get strong polynomiality, or to get faster strongly polynomial and faster Maxwell algorithms for beyond the unit case. Okay. In order to do that, we're going to use an insight about how shortest augmenting paths is wasting effort. Okay. So shortest augmenting paths has two main parts, right? We need to find the shortest path, and then we need to augment it. Right? Now, how long does it take to find the shortest augmenting path? Yeah? That's order m, right? That's breadth first search. And how long does it take to do the augmentation once we found it? Yeah? That takes n, right? Because we just need to update the edges on the path. Okay. So there's an imbalance here, right? Because we do a ton of work to find the shortest path, and then we do much less work to augment it, and then we throw away all of our information and start over. Okay. Now, if you think about it, right, when we look for the shortest path, we're kind of exploring the whole graph. We're building a shortest path tree, right? So why, from all of that work, are we only taking one augmenting path? Can't we get more information out of that breadth first search and maybe use that to do a whole bunch of augmentations at the same time? And so this leads us to the idea of blocking flows. which was a technique developed by Dinitz. This is the same guy as did scaling for Maxlows, so this is a pretty smart guy. But again, Russian, and so people didn't hear about him enough in the early days. Now his work is well known, right? And the idea is to make better use of the shortest path computation. Okay. What we're going to do is recognize that our breadth-first search creates what we're going to call a layered graph. Of vertices by distance. Okay. And what we're essentially going to try to do, and so it finds all the shortest paths. In the graph. Okay, the shortest paths are just the ones that advance one layer at a time and end up at the sink, right? And so what a blocking flow does is that it simultaneously destroys, by saturating, every shortest path in this layered graph. Okay, so in one blocking flow step, you're going to destroy every shortest path, which is going to increase your distance. Between the source and the sink. Okay. So let me add some definitions to make this clear. I'm going to define an admissible edge. Is one which goes, it's a VW such that the distance of W is equal to the distance of V plus 1. Okay? So it's just an edge that is traversing forward one layer. Right? And let me start drawing my example of a layered graph so that we can talk about it. So I'm just spacing out my vertices by distance from S. Okay. And admissible edges are the edges that move forward in the graph. So you can see the admissible edges create a DAG. There are no cycles in the graph of admissible edges. And every admissible edge has an ancestor in the previous layer, because otherwise it wouldn't be in its own layer. Right? So here I've drawn in some admissible edges in my graph. What other edges might be in this graph? What are non-admissible edges? Could there be anywhere? Right. A graph can generally have, can be a complete graph, right? It can have n choose to, but is every edge possible if this is the admissible graph? Yeah?
I think from a node to edges on that level.
Sorry, what's that?
Like from a node, you can have an edge to any node on that level or below.
Exactly. So among the non-admissible edges, I could have an edge that goes to a node in the same level, right? I could also have an edge that goes backwards some arbitrary distance. Okay. But what can't I have? Well, I claim I can't have an edge that goes forwards multiple levels. How come? Yeah?
Because then the distance from the sink is one closer.
Exactly. If I have an edge that traverses multiple levels, then its endpoint is in the wrong level. Right? It should be in a level that's closer to. So that's not possible. Okay? So once I build the admissible graph, I've got these admissible edges which go forward one step. And the fact is that other edges only go sideways or backwards. No edges advance multiple steps. Okay. So now we're also going to define an admissible path, which has the obvious definition. It's a path, an ST path of admissible edges. Now, what can I say about an admissible path? Every admissible path is what? Yeah? Exactly. And vice versa, right? Every shortest augmenting path has to be an admissible path. Okay. Right? Everybody sees why this is true in both directions, right? If it's an admissible path, right, then its length is exactly equal to the number of layers, which is equal to the shortest distance between S and T. So every admissible path is the shortest path, right? Now, suppose that there was a shortest augmenting path that wasn't admissible. What would that mean? Well, that would mean that it is a path that uses a non-admissible edge. Can that be a shortest augmenting path? Okay. If I have any path that uses a sideways edge or a backwards edge, that path is wasting time, right? Each edge of that, right, in the admissible paths, each edge that you traverse takes you one step closer to the sink, right? So if you use a non-admissible edge, you're using one step that does not take you closer to the sink, and you never get it back, right? You can't make it up by using an edge that traverses multiple layers later because those edges don't exist. So any edge that traverses any path that traverses a non-admissible edge is not a shortest path. Okay? All right, so this is our admissible graph, which is a sort of a direct representation of all the shortest paths in the graph. We now define a blocking flow to be a flow that saturates at least one edge of every admissible path. Okay. And intuitively, we're going to have to prove this, but intuitively, what do you think happens if I add flow that saturates at least one edge of every admissible path? Yes?
Becomes longer.
Exactly. If I destroy at least, saturating destroys edges, right? So if I destroy an edge on every admissible path, intuitively at least, this is going to increase the distance from S to T. And that's what we want to do in order to ultimately end up with a max flow. Okay. So let's prove that. after adding a blocking flow, distance from S to T increases. Okay. So how do we prove that? Let's consider an ST path after we use the blocking flow. What edges can be on that path? Well, there might still be some admissible arcs remaining that the flow can use, or that the path can use. But can the path be using only admissible arcs? Right? If there's a path of admissible arcs after I compute my blocking flow, or can there be a path of admissible arcs after I compute my blocking flow? Yeah?
Because then it would be in the blocking flow.
Well, so intuitively, yes, right? If there was a path of admissible arcs, if there's a path of admissible arcs now, if it existed before, then we should have found it as part of our blocking flow. Right? Now, we do have to worry. Could we have created that path of admissible arcs through our blocking flow? Yeah?
When we find the path, we only can reverse edges.
Exactly. So the point is that the blocking flow only uses admissible arcs. And that implies that it only creates backward arcs. Right? So this ST path that exists after the blocking flow, right? It can't be made only of initially admissible arcs. Because that would, if that path was, if all those admissible arcs existed when we were finding the blocking flow, then we would saturate one of them. That's the definition of a blocking flow, right? We don't have any new admissible arcs. Because the blocking flow only creates backward arcs. And that means that the path must use at least one non-admissible arc. Right? And what does it tell us? If the path is using at least one admissible arc, what can we conclude? Yeah?
The distance between S and T increased.
Why? I mean, tell me about this specific path.
Because if it has a non-admissible arc, then it takes like an extra step to get.
Exactly. The path is wasting a step. And so it's not a shortest path, as we said before. So after the blocking flow, right, any path from S to T after the blocking flow is not a shortest path from before the blocking flow. So no shortest paths remain, right? And that means that the distance has increased. Okay? So I mean, very elementary proof, and let's just focus all of our attention on just how do we find a blocking flow, right? If we have a blocking flow algorithm, then running that n times will give us a max flow. Because again, once the distance is increased to n, there's an empty cut, there's no ST path, and so we have a max flow, right? So our big conclusion is that n blocking flows find a max flow. Okay. Now let me pause and just sanity check here. Why isn't a blocking flow already a max flow? I mean, if we're essentially, when we find a blocking flow, we're going to create as we've just argued, we're going to create an empty cut among the admissible arcs, right? There's no longer going to be a path from S to T using these admissible arcs. So why isn't our blocking flow already a max flow? Yeah?
Well, now there's like the old shortest path is no longer the new. Now there's a new shortest path length, which is larger than it used to be.
That's right. I mean, we're destroying all the admissible paths, but there might be longer paths that still exist, right? So we may, traverse here for a while and then crosscut, and taking those crosscuts or those backward steps could let us continue on a path to T. So there will still be paths from S to T, they'll just be longer. Okay? And in unit capacity graphs, right, you can say more precisely that a blocking flow is sort of a maximal flow, right? It's one that you can't add any flow to it on your admissible edges. But it's not a maximum flow because it doesn't pay attention to the residual arcs that get created by the blocking flow. Okay. And as you might suspect, finding a maximal flow is easier than finding a maximum flow, because when you're interested in maximality, you can be greedy. So blocking flow algorithms let us think about greedy approaches to finding flow, and will ultimately give us faster algorithms. Let's see. Yeah, why don't we take our break now? Right, so after break, we'll talk about algorithms for finding blocking flows. But let's get our heads back first. Stand up, jump up and down.
The original proof by contradiction that the distances only go up. We said that if there exists, so if W is defined as the thing that comes before V in instance.
After the augmentation.
Is it possible that the distance to W is defined by some edge that only appears after augmenting the
It's not, and the reasoning comes from the fact that we took the closest edge that got closer, right? If you had an edge like that appearing, then whatever vertex was attached to that edge would be one that got even closer to S than V did.
So this one would get even, so this one would be updated.
Okay, and I mean, this is worked out carefully in the notes. I mean, I was aiming more for the intuition in the thing, but with the notes, you can look at the formulas for D of W versus D of V and see that it works.
I'll think about it. Yeah.
Sure, but I mean, if those things are not clear, ask them in class, and we can spend more time. All right, let's resume. I want to repeat from the beginning of class my meta-logistical announcement. In order to support logistical announcements to the class, we've created a Piazza forum where logistical announcements will be posted. But it wouldn't be very useful to announce the Piazza forum on the Piazza forum, so I am announcing it in class so that you will be able to go find the Piazza forum. We sent an email about it, and it will be on the course announcement page if it's not already there. So far, only about 20 people have signed up for it, so only they are going to get the lucky news when I randomly decide to cancel a problem set. So you should make sure to get on it. Okay. Other just sort of forward-looking logistics, Wednesday is Yom Kippur. I will be out. We will rerun, I expect that we will rerun the same plan as last time where there will be a recorded lecture and you can come and watch it and get questions answered by the TAs here in real time, or you can watch it in your rooms, which is always an option. Okay? There's a chance, if I decide that we've gotten to a point where I really want to be interactive with you, I may cancel the lecture, but most likely there will be a recorded lecture for Wednesday. Okay? But watch on Piazza for the announcement of those logistics. All right, so we have this task of finding blocking flows. And as with MaxFlow, we are going to start building our ideas by looking at unit capacity graphs. Okay. And again, the insight that we're going to use is that, unlike MaxFlow, we can just afford to be greedy. Okay. So if we're trying to find a blocking flow that saturates the edges of that saturates all paths on the admissible graph, what would be the most obvious way to get started? Well, I'd start at S, and what would we do? Well, we want to find a first path from S to T so that we can saturate it, right? So maybe we'll do a depth first search. Right? So we'll start at S, we'll explore out along the admissible graph until we get to T, and now we will saturate the edges on that path. And notice this is a unit capacity graph. So in fact, we will use up all of those edges that are on the path, right? And now we'll go back to S, and we'll start over, right? Greedily advance forward until we get to T again. And now we found another path, and we'll saturate that path. And again, we'll destroy the edges that we traversed. Okay, this is all sounding great so far, but what could go wrong as I continue to do this process? I go back to S, I start searching forward from S. What might happen? Yes? Well, remember, if you think about what we're doing here, we're using the admissible graph, right? We're always searching forward on the admissible graph, which means that we only create backward edges. So we never create a shorter path, right? This is what we discussed about the power of blocking flows, is that they never create shorter paths when you saturate shortest paths. This is also something that came in our shortest augmenting path algorithm, right? Augmenting on a shortest augmenting path never creates shorter paths. Okay, what could go wrong? My plan is start at S, find a path to T, go back to S, find another path to T, go back to S, find another path to T. When is this going to break down? Yes? There are no what?
Admissible paths.
There are no admissible paths. But, I mean, maybe, am I really going to just keep finding paths from S to T, just running forward all the time until I get to T, and I then go back to S? I mean, something can go wrong even if there are still some admissible paths, yeah? Yeah, I might hit a dead end in the middle, right? There's some vertex where I've saturated all the edges out of that dead end, right? So I can't continue forward. So what should I do in that case? what would be the most conservative way to sort of continue my search? I probably don't want to go all the way back to S and start over again, right? Yeah?
You can mark that node as dead and then you go back.
Good. So that node that I hit a dead end at, I can't go forward, but I could still retreat, right? I'll go back to where I came from and just try a different way, right? So essentially, if you think about it, I'm doing a depth-first search, right? I do a depth-first search out of S. If I hit T, I go back to S. But if I get stuck somewhere in the middle, I just continue in a depth-first search pattern, backing up and trying a different direction, right? So let me use some terminology that's helpful for analyzing this. I'm going to start from S, and I'm going to repeatedly try to advance to the next level of the admissible graph, if I can, right? And if I reach T, I found an admissible path. In which case, I will simply augment on that admissible path that I found, and I will restart my search from S, looking for the next augmenting path, right? I'm going to use the term block to talk about this step of saturating all the edges on this path, okay? The other possibility, though, is if I hit a dead end, then I'm going to retreat to the previous vertex on the path and try a different advance. Now, of course, the previous vertex might also have no outgoing edges left, and so I might have to retreat several steps, right? Now, there's another thing that you said, which is very important. If I am retreating from a vertex, I know that there are no further ways forward from that vertex. That vertex is already blocked from the source, from the sink. So I can mark that vertex as dead. Right? And that's going to be useful. So this is basically a depth-first search process. It seems a lot like the process we use for finding an augmenting path, right? But it's not. Or, I mean, it is, but it's not like our process for finding a whole maximum flow. We don't try that hard. In particular, this process pays no attention to the residual edges that are created as we try to build as we try to build the blocking flow. And that means we can prove better time bounds for how long it takes to build the blocking flow. Okay. So what is the runtime of this blocking flow algorithm? Well, there are 3 operations that make up this algorithm, right? There's advance, there's retreat, and there's block. Okay. Now, I'm going to analyze these operations separately. So, again, we've already said we can mark the vertex dead, but if I retreat along an edge, I claim I can mark that edge as dead, right? If I use the edge to get to a dead end, then I know that that edge cannot be part of any further paths, right? So I claim that there are, at most, 1 retreat per edge, right? So let me just make that explicit, right? When we retreat, we're going to delete that edge. Because it can't be used. Okay? So that means that there is at most one retreat per edge. Okay? What about blocks? How many times are we going to block an edge? Yeah?
Is it not the same? Is it also M?
Yeah, right. Once we block an edge, we've used it up. It will never show up again. Okay. What about the advances? Yeah.
Bounce per edge.
Why?
Like the same as before, you aren't gonna like I said, you're only gonna go forward and like retreat. You're not gonna loop around because of the path can have a cycle.
Right, so I'm certainly not going to cycle. I mean, the admissible graph doesn't have cycles to allow me. But might I sort of advance along the edge and then, later on, for some other reason, do a different advance along that edge?
You also already said that you're gonna retreat once per edge, right? So then you eventually need to retreat back to the S node when there's no more paths you can block.
Are you saying I'm guaranteed to retreat from that edge? Eventually? That's not the only possibility, right? Once I advance along an edge, there's two things that might happen. Yeah?
If you advance along the edge, you're kind of committing to either destroying the edge or by saturating it or by deleting it.
Exactly. Once I advance along the edge, right, I'm not going to get back to the beginning of that edge until after I do a block and go back to S, or do a retreat that takes me back to the beginning of that edge. So after my advance, I'm going to either block or retreat. Right? And either of those can only, it'll be one or the other and only once. Right? So I can charge the advance to that eventual block or retreat. And that tells me that there are only M advances. Right? And so, in summary, blocking flow is computed in order M time. Okay. So if a blocking flow is computed in order M time, and N blocking flows suffice to find a max flow, then we have an order Mn time max flow algorithm. Okay. Is that progress? Well, when we were looking at unit capacity graphs in the beginning, right, plane-node augmenting paths runs in order Mn time in unit capacity graphs, right? So have we gained anything this way? Well, in a sense we have, although we can't leverage it yet, but the notion of progress here is a strongly polynomial notion of progress, right? It's just about the distance between S and T, and not about the amount of flow that we're finding, okay? So this is same as plane augmenting paths in unit capacities. But if you think about it more carefully, it's better. So for example, let's consider a non-simple graph. So suppose your graph is allowed to have parallel edges, okay, but is a unit capacity graph. Well, in that case, it's possible for the value of the flow to be larger than n, right? The actual runtime of plain old augmenting paths is order m times the value of the flow, right? And if you have a graph with parallel edges, the value of the flow could be m. So this could be as bad as m squared. Whereas in the blocking flow algorithm doesn't care about the value of the flow because it's focused on the distance between s and t. And so it achieves the mn time bound even if your graph is not simple. Okay. In fact, we can say something even stronger than that. So what we've shown, give this a heading. We've shown that k blocking flows increase the distance from s to t to k. Right? So let's think back for a moment to the argument from maximum capacity augmenting path. Okay? If we have a unit capacity graph with m edges, and the distance from s to t is equal to k, can we bound the max flow? The max remaining flow? In this graph? So remind you of the conversation we had, right? Here's a graph with n edges, right? But it doesn't have n flow, right? Why doesn't it have n flow? Yeah?
They're too far apart.
They're far apart, right? And so every flow path uses up a lot of edges. Now, what can we say then if the distance from s to t is k and there are m edges? What can we say about the maximum flow in this graph? Yeah?
So like bounded by m over k.
Exactly. Right? Because every flow path in the decomposition uses k edges. And each edge is only in one of the flow paths because this is a unit capacity graph. Okay? All right. Now notice that each blocking flow includes at least one augmenting path. So it does increase the flow by at least one. So once we're down to m over k flow remaining, how long is it going to take for blocking flows to finish? Well, that means that m over k more blocking flows are going to finish the algorithm. Again, this is specific to unit capacity graphs, but it certainly is true for unit capacity graphs. So, right, what this shows is that after k blocking flows plus m over k blocking flows, you'll have a max flow. So now what should I do? Yeah?
Set k to square root of m.
Exactly. I can optimize, I can pick k. If I set k equal to root m, this tells me that blocking flows finish in order m to the 3/2 time. Notice the algorithm doesn't need to know k. Right? The algorithm is just run blocking flows until you're done. But this is an argument that you don't actually need n blocking flows. You only need order root m blocking flows. Okay. And this is significantly better than mn, right? In a sparse graph, this is much smaller than mn. And we don't have to change the algorithm. It's just that the analysis is better. Okay. There's a similar observation. Okay. Which says that on graphs without parallel edges, they basically finish in n to the 2/3 blocking flows. And then to the 2/3 time. To find a max flow. And so again, no change to the algorithm, but it just is faster than augmenting paths. Okay. And this one you will prove on your homework next week. It's a very similar argument to this one, but it focuses on the vertices of the graph instead of the edges of the graph being spread out over the many layers. Okay. So blocking flows are already nice in what they do for unit capacity graphs, but our goal is general solutions to max flow. So now let's think about what happens when we introduce capacities. Okay. The basic approach is still valid. Right? I advance as long as I can. If I hit T, I have found an augmenting path. I block it, right? If I get stuck, I retreat. And if I retreat along an edge, I can destroy that edge because it no longer has a way to reach T, right? So the shape is very much the same, but the analysis has to change. So what did we rely on for the unit capacity case to prove our time bounds that we can't rely on in the capacitated case? Yes?
Only be blocked once.
Exactly. Right? In the unit capacity case, when we block, we're saturating every edge on the path. With capacities, right? So advance and retreat are exactly the same. But the thing we have to worry about is that now block only destroys one edge. Of the path. And so we might end up blocking through the same edge many times. Okay. Now, we can still use that, right? We can just charge the n work of that block to that edge. Right? When we do the block. Right? And notice, each edge is only blocked once because you don't ever augment through the reverse edge. It's not admissible. Right? So now, instead of charging only 1 unit of work to every edge. We are charging n units of work to every edge. And so that lets us immediately conclude that a blocking flow takes order mn time. Okay? Which is bad, but is also good, right? Because this implies that we can find a max flow in order mn squared time, right? And if we compare that to shortest augmenting paths, that was m squared n. So we've just replaced m by n in our time bound, which is very important if your graph is dense. Okay? So we have something. Okay? And essentially, we're changing the m to the n, right? So this is exactly what I was talking about as our motivation for blocking flows. Here, we're sort of spending m per augmentation, right? Because we just do one augmentation after doing a whole search for a shortest path. But here, we're replacing that m cost of the augmentation by an n cost of the augmentation because we only have to pay for the edges that we're actually augmenting on, and the search for the shortest path itself is amortized over the construction of that admissible graph. Okay, so this gives us a performance improvement. But in fact, we can make this argument a little bit stronger, right? So to strengthen this argument, let's observe that each block finds a new augmenting path, and so it increases the flow by 1. Yes? And this is true even if we think about all of the different stages of the blocking flow, right? We're going to do a blocking flow where the admissible graph has length 1, and then we'll do another blocking flow where the admissible graph has length 2 and 3 and so on. But each augmentation that happens during any one of these blocking flow steps is going to add to the total flow in the graph. And what that means is that over all the blocking steps, the total cost, over all the blocking flows, the total cost of all the block steps is order n times f, because we only spend n work doing each block, and each block contributes to that total of f that we found. Yes? So until now, we've been analyzing each blocking flow step entirely separately. This is an argument about all of the blocking flows together. Yes, question?
Are you going back to the integer flow case? If we're saying that the
yes, thank you. Let's focus on the integer case. We'll generalize that again once we're done. We're following the same sequence as we did for max flow. Okay. And so that means, right, we've accounted for the blocking steps. We only need to now account for the advance and retreat steps. But we still can say that within each blocking phase, there are only m retreats because we destroy an edge when we retreat, right? So there are still m retreats per blocking phase. Right? And it is still true that we can charge the advances to the blocks and retreats. Right? So if there are m retreats per blocking phase, then that work is order mn over all the blocking phases. Yes? And so if we put all this together, we conclude that even for integer capacities, the blocking flow algorithm finishes in order mn plus nf time, which is equal to order of m plus f times n time. Okay. So that's nice, but it's still got this value of f in it. So how do we get past that value of f? Well, what trick can we use if we have an algorithm that's good for small integer values and we want to generalize it to possibly large integer values? Yes?
Scaling.
Exactly. We can use scaling. Okay. And this is exactly like we did for augmenting paths, right? So we have log u phases. And in each phase, we start with a max flow. We double the capacities and flows that we currently have. And then we add 1 to some capacities. And then we fix the max flow. Now, does anybody remember when we were looking at scaling for augmenting paths, why it worked well? What critical claim did we make about the new max flow that we have to compute that made scaling work well? Right? How do we get that m squared log u bound for scaling augmenting paths? Yeah? Exactly. When we roll in a new bit, the new flow value is less than or equal to m. So what happens if we use a blocking flow to find it? Well, it's going to take us time order m plus f times n. But what's f? Well, f is bounded by m. So this is order mn. So if you're using scaling, a single phase of the blocking flow algorithm takes order mn time. And that means that you find your whole max flow in order mn log u time. And so here, blocking flows really have dominated regular augmenting paths, right? Plain augmenting paths with scaling gave us m squared log u, but if instead we use this cleverer amortization of the shortest path computations, we're able to get that down to mn log u. Any questions? All right, there's an obvious question. What if we want a strongly polynomial algorithm, right? I'll talk briefly about that on Monday, but not in a lot of detail because it requires some real cleverness it took Tarjan to come up with. And then we will move on to a generalization of this problem called the min-cost flow problem. and we will find out why I had to use U for capacities. Okay, we'll finally see what C has been reserved for. So I will see you on Monday. Have a good weekend.